All righty. Okay, so it is definitely a bit haphazard still with things. I opened up the Module 5 instruction, the thing, it probably, let's go to Module 5 in general. It's got the beginnings of the instructional content. It's got some due dates. And now what I did with the due dates, I went almost, I did go every couple of days. Now, I don't have some other stuff in there. And actually, the discussion, you might not be able to reach it yet, just because I have to open it up within the discussion as well as on this page. And this morning I was doing a bunch of the videos for 4.1. Let's see. So the last homework, it says Sunday, October 17th. Now originally that's when we would have liked this this 2 weeks to be done, but of course here it is Thursday and we're just kind of starting into that. I'll try to get things such that probably the due dates will be that Wednesday after that, so that's like the 20th. Okay, so about, a little less than 2 weeks from today. Just like if it was a Monday, then it would be the Sunday, so. And I'll try to get things set up better that way. Okay, I need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Perfect. Okay. Now, so that's probably all I need on that. Go back to this. Okay, thank you, Jordan. I need to look back at your exams. There could be a 4-point swing, mostly in your favor. Number 4C. Now, this is one of these things that my problem was, I liked the problem because of a little nuance in it, but I took this problem from somebody else's past exam, and I'm really sure, I'll have to go back and look, but I'm really sure I did it the way that person had it, and that was something like, the limit as x goes to -1, but from the left. Okay, when I graded your exam, I didn't use that. And so I'll tell you in a moment what I'll do about that when I regrade them. But then this was x plus 1 over the square root of x squared plus 2x plus 1. Now, the tricky part here is essentially what I did, right, is this is just x plus 1 quantity squared, and then you take the square root. So this problem is equivalent to a much more simply stated problem of what's the limit as x goes to 0 of x over the absolute value of x, and then whether you come in from the left or right or just want the whole limit, I could put that on here. But it's really just doing that. And the thing here is, right, the left and right don't match. So I graded it that way. Well, so if you said the limit was -1 or 1, or, I guess it'd be from the left, it'd be -1. So if you said the limit was -1, I said you're wrong. Or at least I'm pretty sure I did. But you weren't. I was. Okay, so I was grading it as the limit, not the left-hand limit. And so I'll go back and look at those. Now, here's what I'm going to do, because it's kind of like giving you too many points or something, that if you said the limit didn't exist, well, you were wrong, but I'm actually not going to take the points away from you on that. Okay? Now, what I will take the points away on, since you get a second chance to fix it, and here I'm telling you what the darned answer is, right? I will take the points away on the first quiz of, so I sent out the announcement, quiz 3, I'm just taking those first 2 pages, and then you can resubmit. So I will, if you were wrong on this problem and said the limit did not exist, or you said it was 1, which is also wrong, then on your quiz, if I had somehow given you points for it on the test, I will take those away on your first quiz score. That just gives you incentive to look through and fix things, right? It's I'm not trying to be mean in that case. I'm just trying to give you incentive. So that, but on your exam, I don't like taking points away that were put on there because I would much rather have you trust that if you are confused, like say, I gave you points for something and you went, I just, was talking to so-and-so and they got this one wrong and they had the same thing. And now you're confused. Well, I want you to be able to ask me about it, right? So, but if I'm threatening to take points away, then people are a lot less likely to ask because they don't want to lose those points. Okay, so on those exams, if I do something like that, and you indeed did get it wrong, now, that's one of those things, if you got it wrong the same way I did, you simply, now, I typed that -1 there, so I knew it was there when I put it in, but then when I graded it, I lost that -1 somehow, or, well, not -1, that negative. But if you just sort of missed it on the exam, you really thought you were solving that problem and you said it was undefined and that's great, fantastic. Okay, you still got it wrong, okay, because you didn't read the problem correctly, but you didn't get it wrong for bad reasons, okay? You got it because your eyesight needs work or something like that. But anyway, so yeah. So I'll try to get those scores redone. That'll, it will, like I say, in some cases it may not do anything for you, but in other cases you'll get 4 points probably, which that's, 4 out of 100. That's nice, kind of thing, or about 4 out of 100. Okie doke. And if you have any more questions on something like that, just let me know. So, okay, so that was 4C. Other than that, and I sent out the question, I asked you to do the survey of 2 days, 3 days, 4 days. I'd still like to know. But actually, we're kind of hearing that it's sort of not up to us anyway to make that plan. So, so I would still like to know what you all think as students. 2 days, 3 days, 4 days under these kinds of plans. What would you think is best? But like I say, and it's kind of out of the math program's hands as to what we do. So, okay. With that, little more business, I guess. That still leaves us a quiz behind. You know, we've got quiz 3, but there was no quiz 4. We'll see. You know, we may just not have a quiz 4. Now, projects, I do want to do the project I had in mind for project 4, but those just may get slid a little bit and we won't have all the projects. We'll just not do as many. Okay, but I really would like us to do that one, but I've got to get it written up for you so you can do it. I don't think it's going to take you a great deal of time, but I don't want to start stacking one thing on top of another and all that. So, you know, worst case is you don't have to do as many such things. Okay, so don't fret greatly about those. Okay, and this way it gives you a little more time. If you are redoing, say, project 2, something like that, then it just frees up a little more time for you to do that. Okay, any questions about anything so far in the class? Yes?
So for the quiz that we're doing, the first 4 questions
Yep.
of the exam, do we just do the ones that we got wrong?
Yes, exactly. Just redo the ones you got wrong, upload those in the quiz spot. So if you go to Module 3 quiz, there's an upload spot in there. And in that sense, don't worry about 4C. Everybody got it right. Okay. Oh wait, no, you do, because I said, yeah, if you did truly get it wrong, if you said either this was had an answer of 1 or undefined, you did get it wrong and you do need to fix that for your quiz. Okay, but if you had -1 for the right reasons, right, you still have to justify it. You do need to submit that with your quiz if you did not have that -1. So, okay. All right. Other questions? Okay. All right. So yeah, we jump into chapter 4, and chapter 4 is, well, at first, just sort of undoing what we've done, in that we have looked at, where's my chalk here? We've looked at derivatives, and now we just sort of want to undo that. And actually, I'd like to point out that this is why you'd like to memorize your derivatives, or at least quite a few of them, pretty well. You want to work on that in practice. And think about you learning some of the math that you know. Okay? Right? You learned stuff like 4 plus 3 equals 7. And you know, hopefully, although it's beginning to look less and less likely, you know, you were really drilled on just being able to know that stuff. You know, 4 plus 3 is 7, and 6 plus 6 is 12, and those kinds of things. Now, why drill yourself on that? You know, why do you need to memorize that? Well, actually, I think you do, because then they went and they did this, right? They said 7 minus 4. And if you get the idea that you had this, it's all the same numbers, it's just where they get filled in, and you had this memorized really, really well, this becomes easy. Okay? Not as easy as this, but it becomes easy. Right? You know, learning subtraction really depends a lot on you knowing addition very, very well. Not the concept of subtraction, but to actually just do it. And then similarly, you got stuff like this, 4 times 3 is 12, and why memorize those times tables so much, right? Well, because then somebody says, oh, well, what's 12 divided by 4? And you say 3, well, how did you know that? Oh, well, because, right? And if, whether you can remember back to that or not, but your reasoning really was because 3 times 4 is 12. Okay, so now what we want to do is, we've learned that the derivative of x squared with respect to x is 2x. And so now we want to go backwards, and we're going to look at that and say, well, what was in there? Right? So our symbol is we use this S-shaped thing. Okay, integral symbol, and then 2x. Now, here, this would be fine. If you just did this, and we never had anything but a single variable here, there would be no real need to toss that in. Okay, but you could also argue back up here, there was no real need to toss in that dx on the bottom, right? If I have x squared and I see the d, I need to take its derivative. Oh, yeah. Okay, but it's still there, and this one's still there. Well, there are actually a couple reasons for it. One is simply that, well, we do algebra. I can stick an a in here, or a y, or so, I need to know which variable I am actually working with in these derivatives and antiderivatives. So, hey, put it there. Let people know. You're being clear in your communication. But another reason is that, this notation actually is helpful that way, because it kind of reminds me I'm looking at that change, a change in a y value with respect to the x value, and this looks a lot like the whole idea of slope, right? A change in the y divided by a change in the x is slope, and that's what this is talking about, is the slope of a tangent line. So the notation is also a good thing, and we will see, it'll take us a couple of sections, but we'll see that actually this notation is a helpful thing to remind me of what I'm really doing. Okay, so here we just want to be able to say, oh, well, okay, what did I take the derivative of to get 2x? Oh, x squared, except not necessarily. Here's the kicker, right? With antiderivatives, I could have had any arbitrary constant. Okay, so when I was in college, I went to a math conference at Miami of Ohio. And I've just always liked this story about the arbitrary constant. So the main speaker, the main invited speaker at this thing was a guy named Hogue, H-O-G-G, statistician, actually. And he was like one of the funniest people I have ever heard. And, he just, he talked about that his family was the hog family until a Fuller brush salesman showed up at the door and said, "Hello, Mrs. Hogue." And then all of a sudden it was the Hogue family. She liked that much better. But he talked about, I think he was at Iowa State University, and he talked about visiting University of Iowa with a colleague there, and they were eating lunch in the cafeteria, and they were discussing which school had the more mathematically literate students. And oh, no, actually, it must have been his school, so they probably were Iowa State. And so they decided, okay, there was, just like we have students who work in the cafeteria. Well, I don't know if we do now, but, we have, so there were students working in the cafeteria, and they said, hey, okay, this young student over here who's wiping off tables and so forth, we'll ask her just a calculus question. And so his colleague who was visiting had to get up and go to the restroom. While he was gone, Hogue grabbed this gal and said, when you get asked a question, answer 2x. Oh, wait, no, it would be an antiderivative, so answer x squared. I'll get the story right one of these days. Answer just x squared, right? And because they had agreed that they just asked, what's the antiderivative of 2x? And so the guy comes back, they get her attention, she comes over, and they say, we just like to ask you a math question. And they ask her, okay, what's the antiderivative of 2x? And she says, x squared plus any arbitrary constant. Ha! Yeah, you don't care. That's awesome, right? So she knew. It turned out she was an engineering student, had a lot of calculus, and they had a great lunch. But yeah, so arbitrary constant, always there. If you're doing this general antiderivative idea, or what we call an indefinite integral, always an arbitrary constant. Okay, it's just always there. Okay, so that's what we're doing. For the most part, we know all the rules. Okay, the only real rule I think that you have to really be careful of, and actually I mentioned on one of your videos, I had to redo the video because I screwed it up so badly, I couldn't just go, oh, yeah, okay, I messed this up, and no, I screwed it up, I subtracted one instead of adding one, so it can happen. But our power rule now is, whoops, wrong symbol. If I want this antiderivative, right, well, how did I get this from a derivative, right? I had taken one away from the power. So when I go back, right, just like I did here, I have to add one. So this is x to the p plus 1. And then, well, this doesn't have any coefficient or anything out front, right? I need to divide by that p plus 1 to get it right. And then, plus any arbitrary constant. And the proof is pretty simple, right? So I make this claim, well, I can prove it. I just use the power rule to prove it, right? So I take the derivative of x to the p plus 1 over p plus 1 plus c with respect to x. And when I do that, well, I can take those each separately and take that constant out. So I get 1 over p plus 1 times the derivative of x to the p plus 1 with respect to x, and then plus the derivative of c with respect to x. So you see, here's a case where it really matters that I've told you I'm taking the derivative with respect to x, because that looks like a variable. Okay, but it's a constant as far as x is concerned. Okay, so I do that, and then where was I? Okay, so equals 1 over p plus 1, And, okay, I take that derivative. Well, that's p plus 1 times x to the p plus 1 minus 1 and plus 0. This divided by that, that's 1. And so I get x to the p. Okay, so it worked. And that's something actually here you don't want to think this is just, I mean, it becomes an obvious thing, I guess. But people tend to forget it. And that is, it's very, very important in these symbols that we realize that if we take the derivative of the antiderivative of some function f of x with respect to x, we get f of x. Right? It undoes what we were doing. Okay? It's kind of like saying, oh, I'm going to square the square root of something. But along those same lines, again, we do have to be a little bit careful, because just like, and that's what I did in that problem where we had the limit in 4C, the square root of the square is a different thing than the square of the square root. Okay? Subtly different. And the difference is I can square a negative number to start with and then take its square root so I get its absolute value. If I start with the square root, I'm only dealing with positive things to begin with. And so then when I square it, I get back exactly what I started with. And so here, similar kind of thing. If I change the direction here, so if I say, well, what's the antiderivative of the derivative of f of x with respect to x? Okay, so there's my function. I took the derivative. And then I want the antiderivative. Subtly different. Right? If I do the derivative first and then take the antiderivative, I always have an arbitrary constant added on. If I take the antiderivative of something and then take its derivative, well, okay, so here I got an arbitrary constant. But then when I took the derivative, it's 0. So it disappears. Okay, so we have this relationship of these things. And when you say, oh, well, I'm going to take the derivative, then I'm going to take the antiderivative. Or I'm going to take the antiderivative and then take the derivative. Yeah, it's like I put my shoes on, I take my shoes off. Right? I just did what I started with. Well, yeah. It is that obvious, but probably you'll forget it at times, right? When that would be an easy thing to use, you'll forget to use it, okay? It just, one of those things in learning, it happens. Okay, so that's the idea of antiderivatives. Any questions so far? Okay, and in 4.1, we pretty much are just sort of stuck with things that do behave as one of the basic rules we know. So, this one, the power rule, yeah, definitely think about that. And then the other place to worry, okay, anytime you see trig stuff, be really careful. Okay, and the reason is that with trig stuff, right, we know the derivative of the sine of x is the cosine of x. Okay, derivative of the cosine of x is minus sine of x. But now you see, when you do that and you do the antiderivatives, so if I want to do the antiderivative of the sine of x dx, okay, here, when I'm doing the sine, it's always great, right? Because when I do the sine, I just get the cosine, no negatives to worry about. Oh, but all of a sudden here, yeah, there's a negative to worry about, because how did I get the sine function? Well, I must have taken the derivative of the cosine. But the derivative of the cosine is negative sine. So you end up with a negative cosine of x plus c on that one. So that darn negative comes to haunt you. Whereas when I'm doing the antiderivative of the cosine, I get a positive sine of x plus c, because when I take the derivative of sine, I get cosine. Okay, so you just trig functions, and so because of the sine and cosine, well, all the other trig functions are just basically made up of sine and cosine. So because of that, then any of the trig functions, you can get these weird negative things going when between derivatives and antiderivatives, and you have to be careful. It's not hard, it's easy to mess up. Okay, and just because you mess up, it doesn't mean you don't understand. Okay, it just means you're being careless. And now it could mean you don't understand, but more likely it means you're being careless. And so you just, when you see trig functions and you're doing antiderivatives, yeah, be especially careful that you didn't actually do the derivative instead of the antiderivative. Okay, so what is it, page 240, 246, I guess. Page 246 has a bunch of differentiation rules and antiderivative rules or integration formulas. Trying to remember your textbook. So there's a insert on the first page, so if you don't have a used textbook that somebody ripped it out of, you also have a bunch of differentiation rules and basic integration formulas on the first couple pages, second page of the thing. And actually, if you look hard enough, you can find in the back of your book somewhere a bigger table of antiderivatives. It's back there somewhere. I don't know. It's in there. And of course, then there's just the web. I mean, you can always Google, do all that. Okay, so most of the stuff in 4.1 then it really just boils down to this. They do one example. Now I've got that on video, so well, I mean they do more than one example, but they do an example 9 where they're looking at physics and position, velocity, and acceleration. And what I'm just going to point out, I'm not going to go through that example, is the relationships that we have between these quantities. We already knew the one direction, I think. So if S of t is position, or some of you with physics displacement, I never noticed before that displacement has cement as the last. That somehow that seems like it should make sense. I don't know. You should be able to make some saying out of that. Then v of t is velocity. Okay, not speed, but velocity. Speed is a magnitude. Velocity is a magnitude with a direction. And then acceleration also has a direction. Okay, so we've got those, and what we know is that s prime of t is v of t, and s double prime, the second derivative, is the first derivative of the velocity, which is a of t. And so then going the other way, if I want the antiderivative of a of t, oh, well, that gives me the velocity plus an arbitrary constant. Now, with simple things where acceleration is a constant, like gravity, in that case, well, this constant that you get here, actually, I'm going to call it CV, that constant you get there is actually always the initial velocity. Okay, it's times 0. Now that disappears if that's not a constant, because things could be more complicated than that. But if the acceleration is just the constant acceleration due to gravity, this first constant is always turns out to be your initial velocity. And then if I integrate or find the antiderivative of this thing, well, and oh, here we go. I didn't think about throwing that in. The textbook doesn't throw that in. But, right, okay, I do an antiderivative and then I do it again. That would be a symbol for that. Okay, and you can do that. And actually, when you get to something like Calculus 3, you see double integral signs all the time. And so you might see something like that. And okay, so this is our antiderivative of our velocity plus CV dt. And so that is going to be our s of t plus, now the antiderivative of constant, using that power rule on 1, is, well, raise, it's t to the 0, so raise that by 1 and divide by 1. And so you get a t here. And then plus the constant that has to do with your displacement s. Okay, now, this is not how you're going to usually see this written, right? You're just going to see this as s of t equals all of this, right? But it's some core function, some basic part, plus the CV t, and then plus another constant that, again, under many circumstances, would simply be my initial position, wherever I am at time 0. And so, it could look like this. And what's this core part usually look like? Well, it's, if that's a constant, then that's just some constant times t. And then if I have a constant times t in here, well, then I get a constant times t squared over 2. So typically this part looks a lot like, a t squared over 2 for most of the problems we do. And, many of you, if you were in a pre-calculus class, you actually used this. They'd say, oh, a ball was thrown in the air, and, and you were just given this parabola to work with, but you've seen this kind of thing before. Okay, so what's happening is you get whatever you would get from, the antiderivative of this original A of t, doing that twice, but then you'll also get some constant due to the velocity somehow, initial velocity somehow, times t plus your initial position somehow from an initial condition. So doing that is this idea of a particular solution. We can, be given a problem and actually decide, choose a particular value of c that solves that problem. So if I'm given f prime of x is equal to x cubed, say, right, and f of 1 is equal to 4, what's f? Okay, well, I can tell you specifically what it is, right? Because I can first say, well, f of x is the antiderivative of x cubed, dx. Okay, that I know just because you told me the derivative is x cubed. And so, using the power rule, add 1, I get a 4, divide by that, 4, plus an arbitrary constant, c. And now, what I know is I can use my other piece of information, that f of 1 is equal to 4. So f of 1 is equal to 1 to the 4th over 4 plus c, but that gives me 4. And so according to that, then, 1/4 plus c is equal to 4. That's 16/4. Subtract 1/4. I get 15/4 for my constant c. And so f of x is x to the 4th over 4 plus 15 over 4. Okay, questions on anything? Okay, so I can find a particular c. I can even be given the second derivative. Now, if I'm given the second derivative, I need two conditions. Okay, because I'll get a constant, an arbitrary constant, every time I do an antiderivative. So if I'm given a second derivative, I'll get an arbitrary constant with the first derivative, and then an arbitrary constant with the function. So I'll have two unknown things. Typically, I need two conditions to find two unknown things. Okay, you could go to a fourth derivative if you wanted to. I don't know why you would, but you could, and you would just need a lot more conditions. You need 4 conditions in that case. Okay. Any questions? All right. Let's take a look at Sage. Okay, now here, now I did a video on this. I solved exercise 44. That's actually the one I screwed up. When I solved it, I had x to the negative 2, and when I did the antiderivative the first time, I made it x to the negative 3 instead of x to the negative 1. Okay, and again, hopefully it doesn't erode your confidence terribly in me when I tell you that, My point of letting you know when I make mistakes is that, yeah, we all make mistakes, and actually the more math you do, the more mistakes you're going to make. I've done a lot of math. I've made a lot of mistakes. Okay? It is going to happen. Now, at some point, you get better and better. I mean, I don't make near as many mistakes on certain things as I did when I was first learning math, this type of math. But it can still happen. Okay? You can still make mistakes. And then, even worse, it's still hard. Okay? Power rule, no. In general, for me, I've done it a long time, it's not so hard. But math is still hard. Okay? I still get frustrated with it. I still am unsure about some answers, that kind of thing when I do it. That is the life of math. So it is not for everyone, but just because you get frustrated or just because you get stumped, it doesn't mean it's not for you. Okay? But again, most people probably don't really want that kind of a life. Okay? So in that way, I would agree, math is not for everyone. But if you're really big on meeting disappointment, yeah, math is a great thing. It really is. And it makes the victories that much sweeter when you get them. Okay. So this problem, it wanted us to look at a derivative of -1 over x squared. And so I'll write it. Well, no, I won't write it down up here since I don't want to go back and forth between the stuff. Okay, so you can see I put fp equals -1 over x squared. That was f prime. And we were supposed to find the antiderivative. But in 44, what they do is they have you create this thing called a slope field. And all you're doing is you're evaluating the derivative they give you at points of x and y. And so, if x is equal to 1, then the derivative of that -1 over x squared is just -1. This is -1 over 1 squared. It's -1. That's a slope field. Okay, so I get that slope, and at each point, x and y, I draw a little short tangent line that looks like that. And if you do that, in this case, you get something that looks like that. Now, I've added the point and the line. There's the actual solution for their number 44. But they ask you to do this slope field. And so I thought it'd probably be worth it here in class to kind of show, not really go through that whole problem, but to show what's going on here. And this is all on the video. You can see this on the video. You can always stop it to see commands. But I declare x, y, and c as symbolic variables. I tell Sage Math, okay, I want to do some symbol pushing here, so I need to tell it that x, y, and c are symbolic. And then I define my f prime. And then I find its antiderivative. And in Sage, one way to do that is, just like we did derivatives, you just do a dot, and in this case you say integral. And then, but with respect to what? X. And then now what you see, now this will say show f here, and you come down, the first thing I did, the antiderivative of -1 over x squared is 1 over x. Okay, add 1, you get a -1, and so that's 1 over x. I had to add the plus c. Sage Math doesn't do it, and I point that out in the video. So again, you have to be careful. You got to remember these things. That that plus c is always supposed to be there. Sage Math doesn't do it. But then, if we forget all that as far as finding the actual solution, down here, this plot slope field, that's all it takes to produce that slope field. Is I say plot slope field, and it's got underscores between the words, and then I have to tell it of what. So I give it FP, the derivative, and I tell it how big to make the grid. Okay, X goes from 0 to 7, Y goes from -4 to 4. And again, in the video, when I first do it, if you don't do the P equals and you just do it and it's the last thing you do, it shows up. Okay, but if you're doing anything else, it may not show up, and so that's why I do the P equal. That's part of the reason I do the P equals, and then I say show P to get that picture. But also what's in here is I go through and I find a particular solution. Okay, they told me the particular solution was X equals 1, Y equals 3. And so I go through and I calculate the antiderivative with the constant plus C. Then I do as I did up here. I set that derivative equal to 3 with X equal 1. And I solve it. And again, in the video, I go through why you need some of these other things attached to it to get the answer. But I can find out what C is. And then I add that C in. I substitute that C in. And I messed that up in the video when I first did it. I figured it out. And I can create that function. So I can do all these steps with Sage Math and just have it do it automatically. And at this point, I wouldn't really have to change much of that to get it to do it for any other problem you would give me. Okay, and that's the great thing about technology, right, is it can do all these things. So again, what do I want you to concentrate on? Yeah, you need to know your rules. You need to know a little bit of algebra. But you mostly need to understand what derivatives mean and antiderivatives mean. Okay, I actually had I realize I'm going a couple minutes over, but I had actually a math major once, and maybe it was in a Calculus 2 class. Could have even been Calculus 3, a little far into the major to maybe be saying this if it was Calculus 3, but I might have been where it was. But he recognized his problem as a math major. He came up to me and he says, I can tell you that the derivative of x squared is 2x, but I don't know what that means. That's a problem. I mean, I would rather you not remember that the derivative of x squared is specifically 2x, but know what it means to find a derivative. What have you done? And so really concentrate on that and allow things like technology to help you concentrate on what all this stuff really means, as opposed to just what are the rules. Okay, because I can replace you real fast with technology if all you know are the rules. Okay, all righty. So what is today? Thursday. So I will see you on Monday.